Today I would like to go ahead and talk about pressure. One of the illustrations that I was taught in high school from I had a really good chemistry teacher, and she did this thought experiment where she said, imagine a cube and you remove all the air from that cube so that there's only one particle within this space, one molecule. What would this molecule do? She said that one molecule would fill the room. So the molecule would bounce around, hitting all the walls, basically filling the space. And the pressure on each of the 6 sides of the cube would all be the same. And the pressure has to do with the speed of the molecule, which is proportionate to its temperature. So by definition, the definition of temperature is average kinetic energy. So if you speed up this particle, it's going to hit the walls at a higher velocity and the pressure will be higher. Now let's imagine a stream of fluid flowing through an orifice. Let me draw this. Okay, so imagine there's fluid and it's flowing in this direction. As the fluid flows through here, because the area decreases, the velocity of the fluid increases. So the other thing is fluid is able to remain uniform in its flow as it flows through the opening nozzle when it's entering the nozzle. However, if you make this angle, the angle of the exit nozzle, too wide, the fluid immediately starts decelerating here. And if you make this angle too wide, the fluid will become wavy like this, and its drag will increase. Its flow will become chaotic. And so over here you have laminar flow, and over here you have chaotic flow. So to minimize this, you just make this angle less wide. So what does this mean in terms of, okay, so the minimum pressure is going to be at this point. So wherever you have the apex of curvature is where the speed of the fluid is going to be the highest in this direction, and the speed or the pressure exerted on these walls will be the lowest. So it's kind of counterintuitive to think that, but it's true. And let me explain why. So remember that particle. Okay, imagine this particle, and now I'm going to give it 2 vectors, one in this direction and one in this direction. Let's just say that this particle is traveling through fluid in this direction. This represents the dynamic pressure. This arrow represents the static pressure. So this can be represented by a diagonal line like this. Now, as you're accelerating these particles, the fluid, the velocity increases. So because of the law of conservation of energy, the length of this vector cannot change. It can't get bigger. The only way for this vector to get bigger is for the temperature of the fluid to increase, but the temperature actually does not increase. So what happens with this vector is as it accelerates, it just changes directions. And now you have a shorter, this vector has to decrease if this one gets longer. So it's just here, let me just exaggerate it more like this. So now you can see that this vector is much longer. It's longer than this one, and this one is shorter. So this vector is in the direction of fluid flow, and that's called dynamic pressure. And so as the fluid increases in speed, its static pressure decreases. Okay, so let's look at an airfoil. If you were going to make an airfoil and you had this length of span here, you have a choice. Let's say you wanted to create a curve on this on the top surface to create a low pressure area. There's two ways to do it. You either put it in the middle or you put it closer to one end. So these are the two approaches. You can either have a symmetrical airfoil where the center of curvature is in the middle, and so the low pressure, the center of low pressure will be at the apex of curvature. So this is the lift. So this curve creates a lift. Now on this one, the apex of curvature is right here, and you'll notice that the lift is not at the same angle. So there's a small amount of drag on both. So if you draw a line in this direction and a line in this direction, you'll notice that on this airfoil shape, the line is behind the perpendicular. So if we draw a perpendicular line to this, the lift is actually slightly behind that perpendicular. And on this airfoil, if we draw a perpendicular line, it's actually slightly in front of it. So this is very important. Now, this does not look like a lot. It's like literally 2 or 3 degrees back and like 2 degrees forward. There's not much difference there. It's maybe 4 or 5 degrees total in the direction of the lift. Okay, so another thing. If this height of curvature is the same on both, there's more likelihood that on the tail end of this, you'll get some separation of airflow, or it'll become wiggly. And because air can enter, can accelerate and remain uniform at a ratio of pretty much 2 to 1. It's the airflow over this airfoil will be uniform over the entire thing, because we've moved the center of, we've basically extended this angle is much more subtle than this angle. So we're taking advantage of the natural flow of fluid and its tendency to be able to pressurize, uniformly, but to depressurize uniformly, it needs basically a longer expanse or a longer run. So if you look at the fuselage of airplanes, the nose cone will look like this, and then you'll see a tail, and usually the tail is almost like twice as long. This is almost twice as long as this rounded front. So that's why the tail is usually more tapered than the nose, or the nose is more blunt than the tail. It has to do with this airflow and trying to keep the airflow laminar. It's called laminar flow as long as possible.